Today we want to take another look at Green's theorem. Let's set up Green's theorem. We have a vector field and we have a curve that's going to act as the boundary of the region R. The curve must be oriented so that the region is on the left. If it's not, if the curve's going the other way, then to fit into Green's theorem, we'll just multiply by -1 and make it go the other direction. So the curve is a boundary of the region R, oriented so that the region is on the left. And then we define this operator on the vector field F called the scalar curl of F. And it's the partial of F2 with respect to X minus the partial of F1 with respect to Y. So if we look at what each of these terms are, when we see the partial of F2 with respect to X, F2 is the function that's determining the J components, the vertical components. So F2 is in charge of the J component, and we're looking at the partial of F2 with respect to X. So how is the vertical component changing in the X direction? That's a very hand-wavy way to think about what's going on in each of these terms. How is the J component changing in the X direction? So that's just how we're thinking about this. How is J component changing in the X direction? And then moving over to the other term, partial of F1 with respect to Y, how is the I component changing in the Y direction? So we're looking at the vector field and we're calculating the scalar curl, and it's a measure of how the vector field tends to curl. Because if we're looking at the J component and how it's changing in the I direction, if we move back and forth, we could imagine the vectors turning. And then we could do the same thing with the I component. I should use the other pen for that one. The I component, so here's I, and then we apply the function. How is it changing in the Y direction? Is it turning, or is it turning like this, or is it not turning at all? So that's very hand-wavy, but it's a good way to remember how the scalar curl is put together. How is the J component changing in the X direction? How is the I component changing in the Y direction? Those ideas will help us remember how to put the scalar curl together. Green's theorem saith the following. So in Green's theorem, we have the line integral of the vector field over the curve C is equal to the double integral of the region of the scalar curl over the region of the scalar curl. So we have a line integral of the vector field along the curve is equal to the double integral of the scalar curl over the region. And so the style of integral that the style of theorem that we have here is that we're evaluating some function on a region by looking at what's going on around its boundary. That's one way we could think of what's going on in Green's theorem. What we're looking at here is, so we're equating a line integral, values from the line integral, and values from a double integral. So here's a line integral and a double integral. Our double integral is going around is over a region, and the line integral is just what's going on around just what's going on at the boundary of the region. And this is something that we do in integrals a lot, because the integral from a to b of f prime of x dx is f at b minus f at a. We're just looking at what's going on over the interval by calculating the antiderivative at the endpoints, which is the boundary of the region inside. So that's one of the ways we can look at Green's theorem as a more generalization. This is why this is one of our fundamental theorems. Any questions? So let's point out some important things that we should carry around with us. Remember that the line integral of a gradient field is equal to the difference in the potential function at the endpoints. So let's take Green's theorem and combine it with what we know about line integrals. So recall that the fundamental theorem of calculus for line integrals, did I just take a true-false test or something? One of those kind of combined F's and T's. So this is Green's theorem up here. The fundamental theorem of calculus for line integrals says the integral over some curve of the gradient of f dot dr. If our vector field is a gradient field, then we just look at the potential function evaluated at the endpoints of the curve. A line integral of a gradient field is just the difference in the potential function at the endpoints. So what this means is that if we integrate a gradient field over a closed curve, a loop, then we get 0. So this means if C, if P is equal to Q, that is, C is a loop, then the line integral of a gradient field will be 0. Because we'd have f of q minus f of q, or f of p minus f of p. So what this means for Green's theorem is that if we apply Green's theorem to a gradient field, we're going to get 0, which means over here, we're going to get 0 for the double integral because they have to be the same. And so what that means is that our curl is going to be equal to 0. So if we apply Green's theorem to a gradient field, then our curl is going to be 0. Actually, this is not really the way I wanted to say this, but I think it expresses it enough. This is actually definitely not how I wanted to say this. I'm glad it got recorded, though. I can white it out all I want, but it's been recorded for all time, and I'm not editing my videos yet. What am I, some kid on TikTok? That's not how I want to say this. So if f is a gradient field, then our line integral is going to be 0. And so that means our double integral is going to be 0. So if we have a gradient field, one way to determine if a function, if a vector field is a gradient field is to look at the curl. If the curl is equal to 0, then we must be looking at a gradient field. So one of the things that we find out when we combine these two theorems together, that's kind of what I wanted to do. When we combine these two theorems together, we can see that the scalar curl of a gradient field is equal to 0. And this is a good way to test if something is a gradient field. I guess I should have just lived with that. So the Green's theorem tells us if we combine Green's theorem with the fundamental theorem of calculus for line integrals, we know that the line integral around a closed loop with, like, for example, a loop that is containing some region, then our line integral is going to be equal to 0. And that means, according to Green's theorem, our double integral is going to be equal to 0. Now, the region R definitely has some area, so whatever we're calculating over that region, that part is going to have to be 0. So we can conclude that the scalar curl of a gradient field, this gradient field, must be equal to 0. The scalar curl of gradient field is equal to 0. And this is a good way to determine if a vector field is a gradient field. So if I hand you a gradient field, look at the partial of f2 with respect to x, and then the partial of f1 with respect to y, and see if there's any curl. No curl, it's a gradient field, and life has become easier. Any questions? All right, I'm going to continue my cover-up. That way you can look at the notes later and be all conspiracy theorist. Look at how much has been redacted. What's he hiding from us? It's kind of like on a test. This happens a lot. So on a test, you'll just be doing one of the problems, and then rather than grabbing your calculator, you just be like, 13. So you just go over here and like, 13 times 7. And then you find out it's 7021. And then you like erase that over here. And then you get your eraser and you're like, I don't want to let you know that I had to multiply by hand 13 by 7. Meanwhile, I can totally see that. I can see that it's been erased. Who are you trying to fool? Plus, do you really think I'm going to judge you if you're like, wait, what's 13 times 7? Anyway, I guess what I'm saying is students be funny sometimes. But it's completely appropriate that you do that because that's the modern society that we live in. Like with Facebook and Instagram and all that stuff, we're not presenting like a genuine form of ourselves with all the mistakes and everything like that. We're presenting a curated image to the world. You know what I mean? I didn't need to record that part, but heck, there it is. And I'm going to leave it in considering I just said we're presenting a curated image. And so now it'll seem more authentic if I just leave that mistake in there. See? Otherwise, I have to rewrite all these notes. That's crazy. Any questions? Comments? Deep thoughts? All right, let's pause the video here and see what's next.